Hello from Chem Help ASAP. In this video we'll demonstrate the synthesis of a tetrazole ring through cycloaddition of a nitrile with azide. We will discuss the reaction, perform the experiment, isolate the crude product, and characterize the material. I am doing this experiment to fulfill a request from a viewer who wanted to see a tetrazole synthesis from a nitrile. Before we cover the tetrazole reaction, let's very quickly talk about a different cycloaddition, the mother of all cycloadditions for intro organic students, the Diels-Alder cycloaddition. This reaction involves a diene reacting with a dienophile to make a new ring. It is an addition because we are adding groups across pi bonds. The reaction makes a ring, so it is a cycloaddition. In general, the reaction is said to be concerted because all the bonding changes occur in the same step. It is a one-step reaction, and therefore there are no reaction intermediates, no carbocations or carbanions or radicals. Because this is the first cycloaddition that many students encounter, it's easy to assume that all cycloadditions are concerted, occur in one step, and have no intermediates. That is not true. The rule for being a cycloaddition is that you need to add groups across a pi bond and form a ring. Alright, here is our reaction. We start with a nitrile. We finish with a tetrazole. We have added something, an azide, across a pi bond of the nitrile to form a ring. This is indeed a cycloaddition. I'm not showing a proper mechanism because I'm not certain that everyone agrees on the mechanism, but most people follow the process on the screen. The reaction begins with coordination of a Lewis acid or protonation of the nitrile nitrogen. The activated nitrile is then attacked by an azide anion to get this type of structure. The molecule then closes to a ring, and we also get a protonation to generate the tetrazole ring. Part of the driving force for this reaction is formation of the tetrazole. This is an aromatic ring. Tetrazoles are not the most common type of aromatic ring, but you do encounter them regularly in drug discovery. The NH of a tetrazole has a pKa that is very similar to a carboxylic acid. In some cases, you can replace a carboxylic acid in a drug-like molecule with a tetrazole ring and improve the molecule's properties. Here is the exact reaction that will be performed in this video. We will start with benzonitrile. We will mix the nitrile with sodium azide and ammonium chloride and heat everything together in DMF for several hours. So we are not using a Lewis acid, but instead a Bronsted or protic acid to activate the nitrile. Once the reaction is done, we'll add some aqueous acid to precipitate the product. We'll isolate the product by a vacuum filtration. Before we start the reaction, let's cover some safety information. Azide is not the nicest material to handle. A risk of azide anion is if you react it with acid, you can protonate the azide and form hydrozoic acid, HN3. Of course, look at what we are doing, heating azide with a weak acid. HN3 can make you dizzy and even pass out, so always keep reaction materials in a fume hood with good ventilation. Also, the waste from this reaction likely contains azide, either as an azide salt or HN3. Azide can form explosive salts with some metals, so the waste should be disposed of properly and not haphazardly mixed with other waste that might contain other metal salts. Okay, let's get into this reaction. Alright, let's get this reaction started. As you can see, I have the morning sun behind me, so the shadows are a little bit bad, but I think we can work through that. Here is a 30 milliliter beaker, and I have probably an oversized stir bar in there, but that'll work fine. So my first step is I want to weigh out our liquid reagent, our benzonitrile, and we're going to put it in this beaker. So let's tare the balance. And here is our benzonitrile. right there. This is actually very nice benzonitrile. It's high grade. You probably don't need really high grade benzonitrile for this reaction to work just fine. I need 2.06 grams of this material, so I'm just going to drip this on here. Now, if I were doing this with students, I would probably have them dispense this with a micropipetter. Micropipetters let you control the liquid a little more. They don't require you to weigh the liquid on a balance. When you're weighing liquids on a balance, you want to make sure you don't get a bunch of liquid on the pan. And when you're learning how to use a balance, it's sometimes hard to not do that. In fact, sometimes I have a hard time not doing that. Okay, we are at, but regardless, since it's just me, I'm going to do this on a balance. We are really close. In fact, we are so close, I'm going to call that is 2.041 grams. I'll record that as simply 2.04 grams. Perfect. Okay, now I'm going to put this aside. We'll deal with that later. But now I want the two dry reagents. The two dry reagents, I'm going to squish down a corner. The two dry reagents are sodium azide. Let's get that first. Here's our bottle of sodium azide. Sodium azide is actually, need to tare first. Sodium azide is actually pretty rough stuff. You just have to make sure you're avoiding acids with it. So we're fine right here, but acids and sodium azide are a problem. We'll discuss that more as we get into the procedure. Let's see, I need 1.56 grams of sodium azide. No, nowhere close. Go a little faster. And this is an excess reagent. It doesn't need to be super exact, but we want to be close if we can. That's 1.2. Oh, that's a big molder. Oh, that's perfect. Okay, that's 1.55 grams, and I want 1.56. That's completely acceptable for what we need. Okay, so 1.55 grams. Let's put that to the side. And now let's finish our dispensing with our last reagent, which is ammonium chloride. And I have ammonium chloride in a much bigger bottle. I'm not going to try to tap it out on the balance. That would be certain disaster. Instead, I'll use a spatula to scoop this out. Oh, come on. I'm not getting much powder out of here. There we go, there we go. Okay. I want 1.28 grams. This is going to be slower than I want it to be. Come on, that was sloppy. Okay, here we go. We're starting to get into some meat here. Okay. We're at 0.67, 0.8. Scooping as fast as we can. You don't want to rush too much because then you just end up flinging stuff everywhere and you got to clean the balance and such. Okay, that's going to be very close. I'm going to go a hair closer. That's 1.25. Let's see what that says. That says that was barely anything at all. That's now 1.26. That's just fine for our purposes. Okay, so 1.26 grams of this material. We now have everything weighed out and dispensed. Let's now take everything into the hood. Well, wonderful. We are now in the hood. Here is our beaker with our benzonitrile, and I'm going to add about 10 milliliters of DMF. I've already kind of pre-dispensed this into another beaker, and I'm going to add the DMF, dimethylformamide. That is our solvent for this reaction, and that is all mixed around. I'm not going to mix that too much because it is in a it's in a beaker. I don't want to slop it everywhere. And I'm now going to add, and this reaction is just as simple as this, I'm going to add the ammonium chloride, and I have this on the weighing paper. I'm going to try to pick it up. Great. And I'm just going to dump that in there. Beautiful. And I'm going to hover this over this stir plate just a little bit. This is getting warm. I don't want to warm it up yet, but I'm going to let that mix. Great. And over here to the far right is the sodium azide. We can pick this up. And we will now add this. Now everything is in the beaker. It's just as easy as that. Okay, we'll let that stir a little bit. And I'm going to bury this into the sand. Now I'm heating this with a sand bath, not just heating it on the bare hot plate. The sand bath gives a little more, infusion of heat from the sides, I'm going to put a watch glass on top, and this is going to heat. Now I have the hot plate set for 120 degrees. You can never really trust these hot plates, but temperature is not a critical element for this. I just want to make sure I'm heating it. The procedure I'm following calls for 100 degrees, so I have the hot plate set a little higher, because normally you don't get full heat transmission into your sand bath, so the sand bath's going to be a little bit cooler. Never trust these hot plates too closely. If temperature is critical, make sure that you monitor your temperature in a manner that gives you confidence. So, I'm not saying distrust the hot plate, but, trust but verify if temperature is a critical element. But we'll be just fine for this particular reaction. So we're now going to let this heat. We're going to let this heat for about 4 hours. I don't know how well you can see in the flask, but that is... everything has not dissolved. There's cloudiness. There's cloudiness in that beaker. There's, so they're definitely solids. Not surprising because it's DMF, not water. We put salts in there. But just take kind of a visual peek, record what you think might be relevant, and then we'll see what it looks like in 4 hours. Okay, well, this reaction has been done. It's been heating for about 4 hours, and let's go ahead and take a look at this. Take off our watch glass, and here we go. There's a lot more solid in there. That's a good sign. We want to see more solid. This reaction should form sodium chloride, and so we definitely see some solids in there. So I think this is done. So we're going to set that to the side. I'm going to turn off of our hot plate. Now let's go through what's going to happen. We're going to take this water, and this is just water, about 100 milliliters. We're going to put it on the hot plate. And yes, the hot plate is still hot, but this will be just fine. Whoops, clink, clink, clink. And now that's stirring. And now we're going to transfer our reaction mixture into the water. And remember, this reaction mixture is our product, plus any side products, and DMF. So by pouring this into water, a large volume of water, we're going to make the solvent much more polar, and that's going to help us precipitate our product out later. So now we're going to pour this in just real gently right in the middle. Let's get that stirring a little more. Got a little purpose to it. Remember, this is DMF and our product being added to water. Doesn't look like it's 100% soluble, but mostly that's still fairly colorless. Now, to make sure, there's a lot of stuff in here. I want to make sure none of that gets left behind, so I'm going to use water. I have about 50 milliliters of water to the side here, and I'm going to use this. Well, I don't know why I'm transferring this by pipette. Let's just pour some in. Okay, great. And swirl this around a little bit, and now I'm just going to try to stir this up with the pipette, and we'll dump that back in. Okay, so again, I'm not really doing anything now, but I'm just trying to complete the transfer. Now you can see there's a stir bar in there, obviously, but there's also a little chunk of solid in there. Listen, that's probably sodium chloride. That's probably not what we want, but I don't want to risk leaving anything behind, so excuse me, I'm going to get in front of the camera. Dump this in. Let's let that stir bar work for a second. Smash that up a bit. Let's just get everything we can in there. Okay, I'm going to say that's good enough. I'm not 100% satisfied, but I don't want to spend a lot of camera time getting those bits of solid. If it's insoluble in water, it's almost certainly not our product. Okay, so now you can see we have a solution that's fairly clear. I mean, it's not totally clear. It's a little bit turbid maybe, but basically everything's in solution. There aren't big chunks of solid in there. So now we have diluted this. This is mostly water. There's about 10 milliliters of DMF in there, so this is essentially a water solution. And now we want to add acid to this, and we want to drop the pH. And in doing so, we're going to ultimately protonate our product, and that is then going to precipitate out. So let's get some of this. Oh, and I haven't introduced this on the side of the hood. This is about 3 molar hydrochloric acid. So we have a decent amount of acid here ready to do any neutralization and ultimately acidification. Now I'm not going to carefully track what's happening here. Normally when you add acid to precipitate a product, it looks like not much is happening, and then all of a sudden you get solid. And it's really not until you see the solid form that you are actually in the pH range that you want. So we're going to keep on adding acid. This is much like a titration. We are neutralizing bases in the solution. And once we get everything neutralized, we're going to see more happen. Now, it is becoming cloudier, and that could be some of our product trying to precipitate out. But right now it's just cloudy. It's just opaque. There's no sign of actual solids in here. Let's add a little bit more, and we'll just take a quick pH reading just to make sure our interpretation of reality is matching what's happening. Okay, so we have a piece of pH paper here. Oh, I see. There is a little solid in there. So let's just touch that liquid. Oh, that's getting acidic. Okay, we are there. We're absolutely, that's plenty acidic. So let's see what happens. And I'm not sure you can see. It's not just cloudy, but they're solid. You can maybe see it best on the surface. Let's move this a little bit. Get the camera working. I mean, that is not homogeneous. There is solid in that liquid. You can kind of see it sticking on the sides. Okay, that is good. Now, I will say one thing. I do have this warming up a little bit. This hot plate is still a little bit warm, and the warmer it is, that heat is not helping our precipitation at all, even though we're getting solid. So this is going to need to stir a little bit. It's going to need to properly cool from any of the heat that I've added. But this is now definitely acidic and definitely forming precipitate. So we'll let it finish its precipitation, but when we come back, we'll want to filter this solid. And as you can see, we have a pretty good volume that we're going to have to filter. So probably a 500 milliliter sidearm flask is what we're going to need for this. Okay, well, what's happened? We have plenty of solid precipitated in here. You can see it swirling with the stir bar. We also have a sidearm flask. Now, I only got a 250. I meant to grab a 5. But I think a 250 will actually work. So what we need to do is we need to seat this filter paper, get our suction going, and I'm going to seat this filter paper. Now I'm not going to, this is mostly water, and I'm going to use mostly water in here, but I've got a little bit of acid in here, because if you remember, we are trying, this is about pH 2 or lower. I don't know if I need lower than pH 2, but I don't want this thing getting too neutral, and when we rinse this, I don't want to use neutral water where the product may have more solubility. I want to try to preserve that acidity. So this is now well seated, and we can just take this and pour this through. That looks beautiful. Oh, it's flowing perfectly. Oh, that's great. Wonderful, wonderful, wonderful. Now, whoops, it's a little loud. Now what I want to do is get some of this dilute acid here. Use that to rinse the sides. Oops, got a little sloppy there. Pour that through good. Now I can't use a ton of rinse, although I might want to, because I didn't use a 500 milliliter sidearm flask. So that's what happens when you forget. You've got to work within the bounds of the container I have. Now if we had to, we could change out this flask, but I don't think it's necessary. Okay, I don't want to put that on there. It's going to make another bunch of racket again. So this is well filtered. It's now drying. Let's see if we can get a little peek in there. I don't know if you can see that solid, but there's plenty of white solid in there. It's mostly pushed around to the perimeter of the filter paper. Okay, that looks good. So now we need to let this sit and air dry, and we're going to go off camera. This is probably going to sit overnight, dry overnight, and then tomorrow we'll come back and we'll get a mass on this and start to analyze it and see if our product is pure or not. It is now later, and here is our dried product taken out of the funnel and spread out to dry on a watch glass. Initially, once I had filtered it, you could definitely smell benzonitrile, and benzonitrile has kind of an artificial cherry kind of smell. But after sitting overnight, that odor is gone. This is a nice dry product. The mass of this product is, let me look at my notes, 644 milligrams. That is not a spectacular yield. That's not going to be a great yield, but the product looks quite nice. So hopefully it'll be pure. We'll have to analyze this, look at this by NMR, TLC, and get a melting point to make sure that what we have is pure. So I would say a low yield, but hopefully it's nice clean material. Let's begin with the TLC and melting range. Here is the TLC. I have a hard time getting good contrast on these TLC plates under the UV lamp. Overexposure is a problem. The solvent is ethyl acetate. That's 100% ethyl acetate, no hexane. The spot traveled 2.6 centimeters, and the solvent front traveled 4.5 centimeters. That gives an RF value of 0.58. That looks good. One spot by TLC is evidence of purity. The melting range was a bit interesting. This compound decomposes with heating, so it does not actually melt. You can actually see the solid partially liquefy and fizz just a bit. So it is almost certainly evolving gas, nitrogen gas, as it decomposes. I observed decomposition over a temperature range of 213 to 215 degrees Celsius, and that's decomposition. The literature value is 216, and I obtained the literature value from Sigma Aldrich, which sells this compound. Okay, so the TLC and melting point both look good. Here is the full NMR spectrum, the proton spectrum. This is the original spectrum I obtained. The solvent for the spectrum is DMSO, deuterated DMSO. Here is the signal for DMSO, and here is water. These two signals are for the aromatic signals. What's missing is the NH from the tetrazole. I thought I would see it in here as a broad but clear signal down past 10 ppm. In some solvents, peaks like this NH are very hard to see, or they become so broad that it is hard to distinguish the peak from the baseline. DMSO is normally pretty good, however, for seeing NH peaks. So, is the peak here? Am I just not seeing it? It is always tempting to explain away missing data by claiming your compound is special or weird. In the chance that the NH peak has a chemical shift beyond 16 ppm, which is very downfield, I reacquired the spectrum with a wider chemical shift range, a broader acquisition window. So note that this spectrum goes from about -3 ppm to 16 ppm. Let's see what a wider window looks like. Okay, this spectrum now goes from about -14 ppm to 26 ppm. Look here at about 17 ppm, way downfield, a nice broad NH signal. So the NH is there. We just needed to open the NMR window a bit. I admit that 17 ppm is the most downfield signal that I can remember in an NMR spectrum. Signals can be further downfield, but this one might be the record for me personally. Leave a comment if you have seen a peak beyond, say, 13 ppm, which is around the limit for something like a carboxylic acid signal. Anyway, it's nice to see that peak. Remember that these two peaks are from DMSO and water. We're interested in these peaks around 8 ppm and this broad signal at 17 ppm. Here is just the downfield region. The NH has an integration of 1H. The aromatic ring has a total of 5 hydrogens. These two are likely the ortho hydrogens, and the meta and para hydrogens fall together right here. Here is the aromatic region. Again, I guess these are the ortho signals. A little bit more upfield are the meta and para-hydrogens overlapping. Regardless of whether those assignments are correct, the spectrum looks really nice, very clean. No stray signals of note. So based on the TLC, melting point, and NMR, this product looks very clean. Let's calculate the yield. Alright, here are our 3 starting materials, the nitrile, azide, and ammonium chloride. The nitrile has a molecular mass of 103.12 grams per mole. We use 2.04 grams of this material. That is 19.8 millimoles. For sodium azide, the molecular weight is 65.01 grams per mole. We used 1.56 grams for 24.0 millimoles. Finally, we have the ammonium chloride. This is actually a catalyst, but let's go through the stoichiometry anyway. The molecular weight is 53.49 grams per mole. We used 1.26 grams for 23.6 millimole. Alright, of these three, we can see that benzonitrile is the limiting reagent. So our theoretical yield is 19.8 millimoles. Well, what did we get? We obtained 644 milligrams of product. The molecular weight of this product is 146.15 grams per mole. Okay, that is 4.41 millimoles of the product. This is our actual yield, 4.41 millimoles. Our percent yield is actual divided by theoretical times 100 for a 22% yield. Well, this is not my best yield ever for a reaction, but I can't complain about the purity. Every 22% looks really nice. I made a tetrazole in a different experiment from many years ago. Probably 15 years ago. I used a different acid in the reaction, zinc bromide, a Lewis acid. I recall getting a much higher yield, like around 75% or higher. So it might be advantageous to use a Lewis acid over a protic acid like ammonium chloride. Regardless, this reaction afforded a clean product, even if the yield was a bit of a disappointment. I hope you enjoyed seeing this example of a tetrazole synthesis starting from a nitrile and an azide salt. This transformation is frequently encountered in the literature. Please subscribe, like, or leave a comment. Take care.